Yeah.
Okay, so
That I would have explained to you.
first of all, thank you very much for inviting us,
And
Felix. Unfortunately, he invited both of us and we couldn't decide who to talk, so you will have to have both of us, but then for a short period.
Like the sort of ones are connected.
Okay. And I was very curious to come here because actually I had a very bright student who then went on to do the, yes, sure. Okay. I had a very bright student who then moved on to do his PhD with Felix, and so I have to now have finally also be here. Okay, so the talk is now, as Stefan already said, this is mathematics. So, but we will okay, how does this work? Can you help me? Is there some magician who can help me with that?
Eines habe ich vorne gelassen. Nee, doch, das ist ja noch. Ich habe ja zwei. Kein Problem.
Ja.
Nee, komm her. Ob du findest den.
Thank you. Okay, so the topic or we are going to talk about is curvature beyond smooth space-time. So obviously curvature is the essential ingredient in GR, but not only there, but also in many of the topics we have seen here already. And then we will talk about two settings. Well, the first one is non-smooth spacetime, where you still have a manifold, which is a smooth manifold, but you reduce the regularity of the metric. And there is, obviously, you have to go below C2 because otherwise everything is just the smooth, as in the smooth category. And there is a lower limit, which is this one locally, H1 intersected L infinity, because this is the largest class of metrics where you can define a distributional curvature in a stable way. And then the second setting we will be talking about is Lorentzian length spaces. This is kind of a parallel to metric length spaces from the Riemannian world. And in that framework, you don't have a manifold at all, but you start out with axiomatically defining causality and time separation, and then you can still speak about curvature or curvature bounds in a synthetic way. Okay, so why should you care about this at all? So first of all, there are physically relevant models, even in classical GR, where smooth spacetimes are not sufficient. Then, of course, the whole initial value problem point of view. And then in the context of the cosmic censorship hypothesis of Penrose, you of course have this interplay between singularities in the sense of incompleteness of the spacetime and the connection to curvature. And then, of course, and this is the main topic here, is approaches to quantum gravity, where you no longer have a metric spacetime and where discreteness becomes interesting. So what is the main issue here and the main message I want to transport is that if you go to lower regularity scenarios, really basic geometric features change, and also, more importantly, Lorentzian causality theory has dramatic changes. And I'm going to give you some examples for that. These are very basic examples to begin with, and then I will be more specific with the others. So the first one is that obviously walking on a cube is completely different from walking on a sphere. And you can always either picture this as the manifold changing, or you could also implement this by just changing the metric and keeping the space the same. So, but it's more vivid to think about the geometry changing. So on the sphere, if I walk on my favorite great arc around, and cross the North Pole, I'm always walking on the shortest path, right? And if I walk on the edge of the cube and I pass the vertex, this is not a shortest path because it's always shorter to go via the side face here. Okay, the second example is a little bit more technical. So this is it appears in a very classical work by Hartmann and Windner from many years ago. And this is best pictured in the following way. So you start out with a sphere and then you squeeze it. You keep the equator fixed and you squeeze it and you make it very cuspy along the equator. So this is my humble try of picturing this, but you have to imagine it very cuspy in such a way actually that the metric is below C11. So the first derivative is only Höller continuous. And what then happens is that the equator is still a geodesic in the differential geometric sense. So the tangent is parallelly transported along it because I didn't change anything around the equator. But this is not a shortest path, not even on the shortest distance, because it always becomes shorter to deviate along in either of the hemispheres because it's so cuspy. You can do this really analytically and convince yourself that this is true. And so this is about geometric shape. Then the next, I move on to Lorentzian causality theory. So once you go to a space-time regularity or regularity of the metric, which is below Lipschitz continuous, then the geodesic equations are no longer uniquely solvable. And in case you can manufacture an example, this was done by Kruschel and Grant also some while ago. You manufacture it such that the null geodesic equation becomes non-uniquely solvable, and then the light cone stops being a hypersurface, but it has full measure. So in that case, all this would be null geodesic coming out of the origin here. And actually, I didn't draw all of them, but everything to the right of this first blue line would be the light cone. And this is something which you would not expect usually. And obviously, this gives you trouble. And then there is also an example of a metric which is Höller continuous, where the chronological future of a point is no longer open. And this consists in you turn the light cones in a non-Lipschitz way, especially on that axis here. The last bit of the turn is not in a Lipschitz fashion. And then you have the blue curve here is time-like, and this connects a point from here to the boundary of its chronological future. So the chronological future is not open. And if you go back to the time when you studied classical GR and you did all this causality stuff, you used the openness of I plus everywhere. So if this breaks down, you are in real trouble. Okay, so now now that I hope I have convinced you that there is really something real going on, I come to a mathematical construction which wants to implement a framework where you can nevertheless speak about these things. And this is now the notion of a Lorentzian length space or your Lorentzian pre-length space. This is something which Clemens together with Mike Kunzinger has come up 5-6 years ago. And this is basically axiomatization of certain basic features of causality. So let's first go to a smooth spacetime scenario, and then you have the causal relations and the time separation. So you say 2 points are time-like related or causal related if they can be connected by a curve which is either time-like or causal. And then you define the time separation as the sup over the length of all curves which connect these 2 points, which are future directed and again causal. And then you can prove that this tau is not continuous but semi-continuous, and that the reverse triangle inequality holds. And this is, of course, necessarily so, because physics tells you have to have the reverse triangle inequality. But mathematically, this is a problem, because if you want to go to a metric setting in the sense of topology, you want a triangle inequality to hold and not be it the wrong way around. Okay, so this is actually the mathematical challenge, and that's why it's in red. Okay, and this is now the definition by Mike and Clemens. So we say we start with a metrizable space. You can think of a metric space, and you define a generalized time function called L, which is a function which takes pair of points and maps you to 0, infinity, 0 included, infinity included, and also minus infinity included, which should be non-negative along the diagonal. And then you can define the causality relations using this L function. So the time-like relation would then be the inverse image of the open interval 0, infinity. And for the causal relation, this is the inverse image of the closed interval 0, infinity. And then the time separation you define by, it has to be the max from L, between L and 0. So here you cut out the minus infinity. And this is, of course, the most stupid way of writing things down, but it structurally doesn't uses a minimal set of data, and that's why it's useful. And then you demand that this tau has to be lower semi-continuous and the reverse triangle inequality. And this is now a definition, and this would allow you basically to mimic basic Lorentzian causality without any underlying structure. You really start out with that construction. So this is basically based on ideas by Kronheimer and Penrose, which go a long while back, and there are also recent approaches which are very similar to this by Brown McCann, Ettore and Stefan, who is here, and also by Olaf, who is also here somewhere. Okay, good. Okay, now this is the definition again, because it's quite a bit. I want you to be able to look back, and I now will give you or tell you about example structures for these Lorentzian pre-length spaces. Of course, a smooth spacetime is of course the obvious example, because this was the model we started with, but this goes down to Lipschitz spacetimes and of course with the usual time separation function. Then Lorentz-Finsler spacetimes, also of low regularity, would be examples, but also, for example, directed graphs. So these kind of directed graphs which are used in causal set theory, for example, give direct examples. And then what you can do with this structure, so you can obviously talk about causal curves and their lengths. You can define geodesics as being locally maximizing causal curves. And you can do basic causality theory. You can establish the causal ladder. You can talk about global hyperbolicity on top of the causal ladder as top stage of the causal ladder. And this works all very nicely in an axiomatic setting. And then you define what a Lorentzian length space is. And this is a property you ask for, which has been fundamental also in the Riemannian counterpart of this construction. Namely, you want the function which you most care about, which in this case is the time separation function, to be intrinsic. That means that the time separation between 2 points should be the sup of the lengths of all curves which are future-directed causal, which connect these 2 points. And this is essential to make this kind of construction work. So if you think of a metric space, now in the sense of topology, this can be ugly things. They can have discrete topology. And one way to get out of this is to really fix in that case the metric to be intrinsic, so to come from the lengths of curves. And this is what is done here as well. And this is a basic ingredient. Okay, so now let me come to talk about curvature. So mainly I will talk about sectional curvature. How I'm doing with time? I'm terribly slow, am I? Okay, when did we start? 5 after, oof. Okay, so I speed up. So sectional curvature, either Riemannian or Lorentzian, is defined here. And there is the catch phrase that in Lorentzian sectional curvature bounds are of no use. This goes back to a result from 79, which says that if this, on a Lorentzian manifold, if this is bounded either below or above, then it's already constant. And therefore, it would not serve as a good condition for geometric theorems as in the Lorentzian world. But this is just because the definition of curvature bound is a little bit more subtle. And this was found out by Anderson and Howard, that in a Lorentzian manifold, you have to say, well, the sectional curvature is bounded below, say, if the space-like sectional curvature is bounded below, but the time-like curvature is bounded above. And this, as simple as it looks, it took a long while to find that. And then there is a theorem by Alexander and Bishop, which tells you that basically in a smooth manifold, smooth Lorentzian manifold, that sectional curvature bounds are equivalent to bounds on triangles, or you can formulate it with triangles. And since I'm out of time, I will just show you the picture. So you have a sectional curvature bound in your smooth manifold if and only if you compare with triangles, geodesic triangles on the zeta space, say, if you have a positive bound, if these triangles have wider opening angles as that for the one direction and in the other direction as well. So this is in metric geometry, this is known as Toponogov theorem, and this is the Lorentzian version, and this is also not that terribly old. Okay, and then you want to turn this into your definition. So basically for a Lorentzian length space, you say you have a curvature bound if and only if the triangles behave in the corresponding way as compared to the comparison triangles in a two-dimensional space of constant curvatures. Okay, and I will basically stop with that. I will give you some glimpse on results. So if you have a strongly causal Lorentzian length space or pre-length space, then if you have a time-like curvature bounded below, then geodesics do not branch. This is something you expect. So this is a kind of proof of concept, because unbounded curvature below always means that the geodesics want to immediately branch off. Completeness is still an obstruction to extendability. So if you have a time-like geodesically complete either space-time or Lorentzian length space, then this is inextendable as a regular Lorentzian length space, which tells you if you want to extend at all, then you will not have curvature bounds from below. Okay, and then finally, there is a splitting theorem, which is also another proof of concept, because that's always some kind of rigidity for any geometry, that if you have a line, meaning a time-like global maximizer, then your space splits into the factor along the line, and in this case, a metric length space with a curvature bound. Okay, and there is also a long list of results, but I will keep silent on that and pass on to Clemens. So.
Okay, thank you. Thank you, Roland. Thanks for the organizers for setting up this nice conference with these very diverse topics. It's really nice and interesting to see. So I will not go into details here for time reasons. I will just continue with the specific topic, which has been on our minds and the minds of different people for a long time. It's actually how to define a right notion of convergence for Lorentzian spaces. Because in Riemannian geometry, this is actually a very powerful tool. And let me briefly recap what we have so far and then go to explain some details. So Noldus defines some kind of convergence for compact spaces But this never really took off because especially Lorentzian compact spaces are not that interesting. And then there are the Lorentzian metric spaces of Stefan and Ettore Micucci, and they defined a notion for bounded Lorentzian metric spaces, and then recently extended this together with Bikov to the unbounded case. Then also Olaf has a notion of convergence for that. There is the so-called, Roland explained before that Lorentzian manifold or a spacetime is not a metric space. But one way to, and our approach was to, say, it's not a metric space, so what else is it? Our approach was it's a Lorentzian preline space, and we can still do metric geometry with that, but building everything from scratch. Then, Somani and Vega, they had a different idea. They said, okay, let's turn our space-time into a metric space. And this is done via the null distance. And then recently, Sakovic and Somani defined a space-time convergence with respect to this null distance. And also recently, there is a paper by Miguel Sanchez and Raul Burgos and Flores, where they have some kind of, in the smooth category, some kind of Giga-Gromov convergence. And our approach is similar to the one by Micucci-Sur and Müller, but there are some differences. But before that, let me recap the Riemannian case a bit. So let's say you have compact metric spaces, XD and XND, and a sequence of compact metric spaces. Then you can define Gromov-Hausdorff convergence by saying that there is a sequence of correspondences, so basically maps from X to Xn, which are surjective in both directions, and they don't distort the distances too much. Actually, the distortion has to go to 0. And that can be reformulated using epsilon nets. So an epsilon net, S, a subset, is an epsilon net if you cover your space with balls of radius epsilon. And then you can show that actually Gromov-Hausdorff convergence is equivalent to demanding that for every epsilon, there is a finite epsilon net such that, so I find epsilon S in X and Sn in each of the members of the sequence, such that the distances of these points, they converge. This is enough. So, and that is really powerful in Riemannian geometry. So Gromov's p-compactness theorem, for example, tells you that if you have a class of compact metric spaces which have uniformly bounded diameter, and you can uniformly bound the cardinality of epsilon nets you need to cover each of the members. So you say, okay, you have a large class of compact metric spaces, but you know that each of them you can cover with 100. So given an epsilon, you can cover it with 100 balls of radius epsilon. Given a different epsilon, a small one, say you can cover it with 1000. And this is enough for all of the members of this class. Then actually this is pre-compact. So this has every sequence has a converging subsequence. And for example, how this is used in geometry is that if you have a sequence of compact Riemannian manifolds of the same dimension and they have sectional curvature bounded below by the same constant, or actually Ricci curvature bounded below by the same constant is also enough, then there exists a converging subsequence in this Gromov-Hausdorff sense. Of course, the limit you get will not be a Riemann manifold, but it will be a metric length space. And for example, it will have sectional curvature bounded below in this triangle comparison sense. Or it will have Ricci curvature bounded below in the optimal transport sense. So you see this is very powerful in Riemannian geometry. And this is, for example, you get Alexandrov spaces. These are metric length spaces with sectional curvature bounds. Ricci limit spaces are exactly limits of such sequences, which are not Riemannian manifolds necessarily. And then you get CD spaces. So these are metric measure spaces have Ricci curvature bounded below. Yeah. So, and for different reasons, in Lorentzian geometry, you would like to have such a notion of convergence or a notion of distance. But since, as explained, the Lorentzian manifold or a spacetime is not a metric space, you cannot just apply this. You really have to come up with something new. And also, what is the setting? So for us, of course, it's the setting of Lorentzian pre-length spaces. So here I just want to briefly explain what is a correspondence, but maybe for time reason, I will be rather quick. So if you just have two sets, X and Y, a binary relation R is just a subset of X times Y, and a correspondence, it is a correspondence if for every X there exists a Y, which is in relation, and for every Y there exists an X, such that is in relation. So if you project to the first factor, you get all of X, and if you project to the second factor, you get all of Y. Then you can define the distortion between two of a relation of a correspondence between two Lorentzian preline spaces or also metric spaces, but just looking at all the pairs which are in correspondence and look at the difference of the time separations. Also, you can compose correspondences, and if you do that, then actually it's sub-additive, so the distortion doesn't increase if you compose it. And then this is joint work with Andrea Mondino. We define a notion of Gromov-Hausdorff convergence for Lorentzian preline spaces, and now the idea is that to replace the epsilon nets we had before, which were in terms of balls, by causal diamonds. And one difficulty is, of course, the ball has a center and a radius, but a diamond has two vertices, and how they are related so there is a lot of more freedom how the vertices are related. So, and we say in the Lorentzian preline space, a family of causal diamonds is an epsilon net, but first define what is the set of vertices. This is really just if you have such a family, these are the pi's and qi's. And then an epsilon at S for a subset A is a collection of causal diamonds, such that the time separation of the diamond, which is really just the time separation of the vertices by the reverse triangle inequality, is less than epsilon, and the union of the diamonds covers your set A. And in the metric case, if you have an epsilon net, then it automatically covers your set. So here you have to demand that additionally. Okay, and then we can define convergence for subsets. Okay, so you have a sequence xn, ln of Lorentzian preline spaces and the limit xl. So this would be the limit, or actually you first do it for subsets. So an is a subset of xn and a in x. You say that an converges to a in the Lorentzian Gromov-Hausdorff sense. If for all epsilon there exists large n, such that and finite epsilon nets S for A in X and Sn for An in Xn, such that the cardinality is the same. Then there exists a correspondence Rn of the set of vertices to the set of vertices of S, such that the distortion goes to 0. So the first two are analogous to the metric case, but then you have to additionally assume two things, which in the metric case are automatic. Namely, that you can extend a correspondence of 1 over L net to a correspondence of 1 over L plus 1 net, so making it smaller, but without increasing the distortion too much. And also, you demand that you have that the vertices are forward dense, so that if you demand by this V, the total set of vertices, then for any X which is not already a vertex, you can approximate it by a sequence of vertices such that they are causally related like that. So they come from the past and converge monotonically to this vertex. And again, this is automatic in the metric case. If you have for every epsilon an epsilon net, then it's automatically dense in the metric sense. Then you can approximate every point which is not already in this epsilon nets. You can approximate by members of the epsilon nets. And also we can strengthen this here to strong convergence if we demand that actually these points here are time-like related. Okay, then another difficulty is that there is no canonical cover of a Lorentzian manifold or spacetime. So if you start out with a metric space, you fix a point, then you immediately have fixed a canonical cover by just looking at balls with increasing radii. But in the Lorentzian case, there is nothing like that. So you have to specify a cover as an additional data for the convergence. This is what we call covered Lorentzian preline spaces. And basically, the only thing you should take away here is that we had this convergence for the subset, Now you specify the cover, and then you demand that each of the covering sets converges in the sense of the subsets. And then you can really show that this is a definition of convergence of spaces. Okay. So how about time?
We're done, but maybe 2-3 minutes.
Okay, so then just let me mention that we have a precompactness theorem which holds for family of globally hyperbolic smooth spacetimes with compact Cauchy hypersurfaces. We can show that such a class is precompact, so every sequence has a converging subsequence. But maybe I will end with some outlook on quantum gravity, because this is really in theme of the conference. So in positive signature, as Roland explained, you have this triangle comparison techniques to define sectional curvature bounds, but actually you can also define sectional curvature bounds for discrete spaces. And also you can define Ricci curvature bounds for discrete spaces. There's, for example, this Olivier-Ricci curvature. And our colleagues in Vienna, Beran, Kunzinger, Rott, and also Beran, they did something for time-like sectional curvature bounds for discrete spaces via the 4-point condition. So you have, for triangle comparison, you specify a triangle, and then you say, okay, you have to compare distances on the sides. So for that, you need curves to have the sides. But if you're in a discrete space, you don't have the curves. So what you do is, which is this 4-point condition, which also comes from metric geometry, is that you specify you don't specify a triangle, you actually specify a comparison situation. So basically, you specify a triangle and a comparison point. And for that, you don't need curves. So this works also in the discrete setting. And for example, this applies for graphs or lattices. So for example, for discrete causal fermion systems, I saw yesterday, this is treated in the book by Felix, Sebastian, and Jan Hendrik in this section 5.2, but also for causal sets where this discreteness is built in from the beginning, but there are other approaches to quantum gravity where discreteness is fundamental. So you could also talk about time-like Olivier-Ricci curvature, and this is work in progress by our colleagues, our postdoc Samuel Borza and 2 PhD students, Joe Barton and Jona Röhrig. They want to define an Olivier-Ricci curvature in the time-like sense, which is the analog of this notion for discrete metric spaces. And then in principle, you could compare different notions of curvature in different approaches of quantum gravity. Of course, the catch is that what this would compare is like what we think is the curvature given this geometric thing, but each approach has probably its own idea what should be the curvature. But still, it might be interesting to look at it from a more geometric point of view. Okay, and I give some references, I end here. Thank you very much.